All right, our final speaker is Seungbum Kim from the NASA Jet Propulsion Lab. He's going to talk about high resolution soil moisture over forest mountains using airborne and satellite radar.
Hello, everyone. I'm Seungbum Kim from NASA JPL. My co-authors are Eric Fielding from JPL and Tina Liao and Mohammed Krum, University of Georgia, and Mike Kosh, and also USGS William Schultz. So thank you for including me in this program. So the previous presentation gave some introduction that we need a high resolution soil moisture. So I'm going to elaborate on that. Yeah. So I'm a remote sensing person. So my understanding of forestry is mostly coming from my trail running and hiking. So if any of the things that I say are unwarranted, then I'm open to change. So, so from my view, soil moisture in the forestry is an antecedent indicator of fire. We all know that. And also it's a posterior condition for subsequent disaster, like the landslide. But currently, as mentioned in the previous talk, remote sensing solutions are quite limited. The resolution is about 9 kilometer, 20 kilometer. And there are high resolution radars like Sentinel, but they are not sensitive enough of soil moisture. They have 5 centimeter wavelengths. And what I mean is that this is some schematic of boundary between air in green and soil in red. There are tree trunks, branches, leaves. So radar signal, they go and try to get the soil moisture, but the physics tells us that if the wavelength is similar to the size of element, then it cannot really penetrate. So we know that the trunks are 5 centimeter, leaves are 5 centimeter, and so on. So C-band is not quite best tool for this, but L-band, which is about 22 centimeter, has a much better chance, as I will demonstrate later. And then the spatial resolution. So it matters, especially when there are openings between trees and there are shades. So this is one effect of remote sensing spatial resolution. This is the agricultural domain soil moisture retrieval at 18-meter resolution. We can tell the canal, road, this patch of very wet. Wet is blue, dry is yellow. We see different fields have different moisture level. If we upscale to NISAR's 200 meter, we can still see most of these features, but when it comes to 1 kilometer, 3 kilometer, we lose a lot of this resolvability. And this becomes a problem to my thinking, is that, so this is about 100 meter opening in the tree, in the forest. And I'm guessing that the soil moisture in the lower ground is a bit higher than the slope. And also, so if we don't resolve this scale, then the soil moisture, this part and that part will be averaged, and it can underestimate the forest fire risk. Similar happens in this one. In this case, this is a Big Sky, Montana. There's a mountain ridge. I think Bill Gates' mansion is somewhere here. And so this part is the southern south facing, and we all know that the south facing slope is very dry. That's why we don't see many trees, but north facing, they are wet, so have a lot of trees. And like this map, 9 kilometer, they average all this out. So the moisture from here and there, they will be averaged out, again, underestimating the risk. But if we have a spatial resolution of, say, 100 meter, or I'm going to show some 6 meter, then we can tell all the differences. So from now, I'm going to show some of the examples that this radar can estimate soil moisture reliably. This one example is the Airborne field campaign in Canadian aspen forest. The forest looks like this. So there's a quite dense understory. The aspen trees, they are very mature. And then this is the radar image. Some of these polygons are the boundaries. The red ones are the in situ samples. So we get quite extensive in situ samples. So statistically, the comparisons that I'm going to show here are quite reliable. So the soil moisture retrieval in Y and in situ soil moisture in X, they go hand in hand. RMS is about 0.03, 0.04, quite good. So this can be a bit surprising because people have reservations about being able to map soil moisture over forest. But I don't think this success is accidental. It's because this happened over 1 month period, so the vegetation didn't really change. But soil moisture, as you can see, changed from near dry to completely saturation. So L-band being able to see through the forest to a large extent, and the vegetation doesn't really change much. Looks like we are able to map the soil moisture in this rather dense aspen forest. I mentioned a lot about high resolution, sometimes 6 meter, but then the previous result is also 6 meter spatial resolution. Is that accidental that we get 6 meter? To answer that question, I did some Monte Carlo simulation of the retrieval process and trying to confirm that this 6 meter is something that we can achieve in this simulation. So X is vegetation water content in kilogram meter squared. So most of forest lies somewhere 10 kilogram or above. Y is the retrieval RMSE of soil moisture. There are 4 types of trees, and deciduous, the vertically oriented trees support pretty reliable retrieval, but like the tropical forest where the trees go in all, trunks go in all directions, we don't have that good capability. So at least if I aggregate the radar image at 6 meter resolution from Airborne or about 60 meter from spaceborne, this simulation indicates that I can achieve this accuracy, and experimental data supports that. So this is a second example. In this case, it's a pre-fire condition. And now it comes to the opening. So this is the domain, about 300 meters, 300 meters in Northern California, where forest fire is occurring quite frequently. So we took a radar image over the period of 3 years, and this dot is where the station is. And you can see that first, temporally, there is a realistic variation in soil moisture. In summer, dry, winter, wet, summer, dry, temporarily, but also within this 300 meter domain at 6 meter resolution, we can tell quite a realistic variation in soil moisture. So with this information, we can tell with a capability that some part of the region is more likely to catch fire, other parts, they are not. And this is the end of the day. So just to as a refreshment, this is a 15-degree slope. So usually remote sensing like SNAP, 15-degree slope, which is pretty steep, is all averaged down. But at this resolution, we can resolve the slope, and we were carrying the roughness board on this 15-degree slope in summer, which was quite an ordeal. And the next one is the post-fire condition. So this site is the California Highway 1, Big Sur, and we often have a mudslide and rock slide closing down the highway. So this has happened about 2 years ago. After the fire, rained, and rock slide closed down the Highway 1 for almost a month. So we installed a sensor after the forest fire. You can see that because of the fire, all the trees were burnt, and we have airborne radar mapping. Then if I compare our retrieval with in situ, they agree pretty well. The bottom is the in situ at about 6 different steps. So we want to look at this blue curve over about 6 months period. In summer, it was very dry, but then it rained, and then soil moisture spiked. That is captured well by the retrieval, which is shown by blue crosses. In situ is red star. They go hand in hand. I still have to retrieve from the logger manually the data for the next 3 points. That's why I don't have in situ here. So the point here is that post-fire condition looks like this experiment shows that we can map the soil moisture reasonably, so help us to prepare for or predict some of the things that may happen after the fire. So summarizing the platforms, think I have one. Okay. Summarizing the platforms of the experiments that I showed you in the past, one is the L-band airborne radar. It costs about 2K to 5K per flight, and 6-meter resolution if it supports the surface. L-band NISA is going to be launched next year. The resolution 200 meter, about 6-day revisit. This will be offered as a standard product at no cost. But there will be also 60-meter resolution doable, I think, and about at some locations 3-day revisit. But this is not provided as a standard, so that there has to be additional funding to do to generate this one. And then my last chart before summary is another platform, which is X-band satellite radar. X-band is just 1 centimeter wavelength, so it cannot really, we don't expect that we can do soil moisture when there is the sizable amount of vegetation. But M3E, which is radiometer, it was able to map the soil moisture at X-band. And then for forestry, what I'm thinking, I just started this investigation, so I don't have a good validated soil moisture data yet. But this is the Tifton USDA location, and there is the trees planted manually with gaps. And this satellite offers 6-meter resolution, same as the Airborne. So even if it's a satellite, it has a really high resolution. And with this resolution, I believe we can distinguish the trees versus opening. So, and that's shown by the radar image shown here. So we can see that where there are trees is white, where there are openings is dark. So my expectation is that even if I cannot do the soil moisture where trees are, I can do where there are opening. And this is situation and capability, I guess, can happen in the mountain terrain as well. That means this high resolution satellites can possibly provide the information that we need over real forest. So I'll summarize that I showed the examples that we can estimate surface soil moisture at about 0.06 accuracy over aspen forest, mountain slopes, openings, and in the conditions of pre and post-fire situations. And I got motivated to join this workshop when I listened to the presentation about 2 months ago about US webinar on forest fire mitigation. And there was a topper fire tool, which takes in about 200-meter resolution database. So this capability can contribute to that tool. And these are just a summary of what we have available. So I'll end here. Thank you.
Questions for Seungbum?
Hi, Saab. I was just wondering, what was your X-band? Was that Capella SAR or?
Yeah, it's ISAR.
Einstein?
Yeah.
Oh, I'm not familiar with that.
Yeah, it's similar to Capella SAR.
Thank you.
So a quick question. I heard you mention assigning some fire risk rating to what your readings are in terms of soil moisture. I'm wondering what type of risk rating system and correlation are you associated with?
Yeah, so the question was what impact or contamination rain events may have, is it right?
No, I'm asking, you were suggesting that you could assign a fire risk rating to the readings you were getting for soil moisture.
Mm-hmm.
And I was wondering what risk rating system and calibration were you using, or is that something that you're looking for?
Yeah, I would relate the soil moisture level to the fire risk rating, and the soil moisture will be one input, and the vegetation, the fuel will be another. So does that answer your question?
We can talk later. Thanks.
Marena? Marena? There's a question back there.
Hi, thank you for the talk. Do you plan to do the same with C-band with Sentinel-1? Is that an option?
Yeah, we do C-band Sentinel-1 based retrieval, but over forest, because we know the limits. So especially the NICE are coming on board very soon, and the aircraft L-band available. So unless there is a real urgency, like the Maui last week, I wouldn't really, I haven't spent much time on C-band.
Okay, thank you. That concludes this session, and Mike has some announcements.